Hello everyone. So today we are in the second session of nonlinear dynamics and chaos. And as you already know, I'm following mainly the book of Strogatz. So feel free to go and check it as well as a complement to the slides and the class and these videos. Okay, so last time we were talking about, or we will talk about for the entire class, about nonlinear ordinary differential equations. And we saw that we may have first order, second order, for example, for the pendulum. And if we want to capture chaos, we need three differential equations, so 3 dimensions. And today we will start with the fundamental one, which is first order differential equations, so basically one dimension. And this is why we talk about flows on the line, because it's one dimension. And this is the simple case we were just exploring. So this is the x dt, so the change of x with respect to t, and fx can be a nonlinear function in x. And an example can be this one. So x dot equal sinus of x. So when you have this thing and someone tells you, tell me the evolution, tell me the dynamics of this x. So the function, you have an initial condition, and then you want to know where the solution x is gonna go. Actually, it's pretty tough, no, from nothing. So you actually may want to derive an analytical solution, and you can do that, and you obtain, for example, such a situation when you have here the initial condition of x, and basically the equation is, let me just give me a second. So here we have this is t, this is x, and this is the initial condition x0. So the question is how this is going to evolve. It's gonna go like this, it's gonna go like this, it's gonna stay the same. And from this equation we can know that, but not super clearly, because we have to see that this is an actual implicit equation, because we want to have the function of x with respect to t and not of t with respect to x. So we would like to have the other ways around. Okay, but it's not easy to explicitly have this relation x function of t, and still it's very hard to have like imagine an asymptotic behavior. What happens when t goes to infinity, x goes to a given equilibrium point, will go away, what will happen? So this is just to make you aware that such a simple equation like this one may have analytical solutions that are not super transparent to be treated for an analysis of the dynamics of the system. So in that sense, we have trouble, no? So not all analytical solutions are transparent, and actually most of the time you don't have even analytical solutions, so you have nothing. And maybe a good strategy is to go and have something else. Let's now perform a graphical analysis. So we have here the same problem. We have x dot equals sinus of x. We have here, now we define an axis which is going to be x, and the other axis is going to be x dot. And we just make the corresponding graphic representation of this function, and which is that's all. So we have the sinus. Okay, so now imagine we have an initial condition x not here, so this is going to be x0, and you want to see what is going to happen. So let's analyze this. This point in here exhibits a velocity because we have the x, the t, sorry, and the velocity is actually positive. If it's positive, it means that the position of the particle will change, or will increase actually. And as it changes, you will have here maximum velocity. So this position in the moment of the crest here of the function. And then it will keep increasing because the velocity is still positive. But as it increases, so the position of x gets larger, you will see that the velocity is little by little decreasing. And little by little it goes towards 0. Asymptotically reaches this point. And once this is reached, it doesn't move. Now imagine you have a perturbation of this point. It will go away from this point, but following the same reasoning we just did before, it will go back to the fixed point. So we have here this point, and we will recognize it as an equilibrium point, or let's call it also fixed point. This is the jargon used most of the time. We have a very similar situation when we analyze an initial condition close to this point in here. So let's have this example. In here we have this initial condition, let's say, and now you will see that the velocity is actually negative, so x dot here is negative, therefore the position will go to the left. If we go to the left, the velocity will be here maximum, and then some, let's call it, let's say, the minimum, then the absolute of the negative velocity is going to be maximum, is what I meant. And then the velocity will go little by little towards 0. So the displacement of the particle is going to go to the left, but every time in a slower manner, until you reach again the equilibrium position, which is our fixed point. So here we have a fixed point. And basically you just saw that if I'm in this position here, I will go to this point. If I'm in here, I'm going to this point. Now if I have a perturbation and this particle for some reason is in here, you will see that the velocity here is negative, therefore the particle will move to the left every time in a slower manner until reaching again the equilibrium position. So any perturbation you do around this point, the perturbation will be smaller with the time, and then the particle will go back to the equilibrium position. Here we have another thing actually that we didn't discuss yet. Imagine you are able to place that particle that I'm talking about at the position x equal to 0, exactly this position. This is going to be the actual initial condition, okay, in here, in this position here. So the velocity at that position is 0, which means that the particle will stay there forever. This is exactly the same situation as if you place the particle at the initial condition being in here or being in here, the same situation, with a very big difference, that a little perturbation in here will get the particle away from this initial position x equal to 0. So any perturbation will make that this particle move towards this position or towards this position, depending on the sign of the initial perturbation. So now we have seen that we have two different cases. We have equilibrium points that are unstable. Which one is? Think, which is the unstable equilibrium point? Yes, it's this one. And these ones are stable. So this is gonna be, in our jargon from now on, a unstable fixed point, and this is going to be a stable fixed points, which in another way of terminology, this is going to they are going to be attractors, and this is going to be a repeller. This is the way of representing the stability with these arrows, okay? And see that the repeller here is an empty white dot, and here a full dot is going to be the representation of attractors. Okay, so now let's go back to the first equation we were interested in. What is gonna happen given an initial condition when time goes to infinity? So let me just write here, this is x dot, and this is something that you can do also behind your screens. So let's do it together. So we'll have this plot like this, and we will call this t, and we will call this x. Now we will draw the fixed point. So the initial condition, if you remain here in this fixed point, then okay, just let's remember this is basic trigonometry. So this is gonna be equal to pi. We just project this in here. It's going to be 2 pi. It's going to be 0, and so on. Okay. Well, if I draw this, it's going to be pi. Okay, now we have all the lines of the fixed points, and we will do the first experimental thought. We will define an initial condition being in here. Okay, so this is just a little bit lower than p, so somewhere in here. So the thing we already discussed is that the particle will go towards the fixed point here in black that is placed at pi. So we will have something like this. It will stay there forever. Now what happens if, let's find another fixed point, let's place it in here. So it means that we are very close to 0 in the negative region here. Okay, So the most of the time the assumption is something like this. So just that will go towards minus pi. Okay. Something like that. Is this correct thing behind your screens? Or there is some like a detail that is being missed? Yeah, actually there is a detail that is being missed. What is the detail? So I have to write the whole thing. Okay, it's just something that might be also important. Remember that in this moment in here the velocity is very small. Here the velocity is high, so negative, and then it's gonna get smaller, so the absolute value until it goes to 0, which means that at the beginning you will have an acceleration. So you don't have a small velocity, then you have an acceleration, and then goes back to equilibrium, something like that. Okay, so this change in slope represents when you have a small velocity, the velocity, so the absolute value is maximum, and then it goes again smaller until asymptotically it reaches an equilibrium. Just write it until here. Okay, and now basically you can think the same way for the other points. So you want to go something to pi and so on. Actually, what is going to be the next fixed point that is an attractor? So basically it's gonna be pi. 2 pi is gonna be a repeller. So we will have to go until 3 pi to have another attractor. Okay, so maybe you already got an idea behind all this, is that the slope somehow defines if I have an attractor or a repeller. So in this case the slope of the function is negative, and this is associated with an attractor. In this case the slope is positive, here is also positive, and this is associated with a repeller. And this is something we will just derive in a more formal way mathematically to define what an attractor and what a repeller is. So this is also shown in the book of Strogatz, so you are free to go and look at the corresponding sketches and the explanation in there. We will now analyze this problem. This is a circuit, and we will want to know how the current behaves once this switch is put on. So how is going to be the flux of current? So the question is, how can we just plot something like time and current? Or actually we can be interested, instead of the current, on the actual charge on the capacitor. So here the charge in the capacitor, so how fast it will charge. And we can start from an initial condition when we have no charge at all, and then you just switch on, and then we just check how the charge of the capacitor goes, or if it doesn't charge at all, what happens. So we'll just write the relations from our sketch. We will just write this like this. We have the voltage, not, and the voltage, call it R, and over the capacitor. So our equation is based on this relation. V naught is equal to VR plus Vz. So this is all what we need to know. So from your class on electromagnetism, maybe you know how this relates with resistance. Think? Yeah, okay. Everyone is right, is IR. And now this one is maybe not as easy to remember. So the voltage on the capacitor is proportional to the charge Q and inverse to the capacitance C. Okay, and the last relation we need is to know that the charge, so the current, the definition of the current, so is equal to the change of charge with respect to time. Now if we equate all this, we will have V0 is equal to IR plus QC. V0 is equal to dQ dt R plus QZ, and we want to have a differential equation for Q. You already somehow realized about that. So if I rearrange that equation, I will get the Q dt R equal to V naught minus QZ, which is nothing, so we'll just put it in here. Q dot equal to V0 over R minus Q over RC. So once we have the differential equation, we can start drawing, which is the objective this time. So we draw, and the first thing we want to see is how can we express this as Q dot equal of F of Q. And if you remember from the example of the sinuses, the fixed points are defined when the function, in this case a function of Q, is equal to 0. Okay, so fixed points and normally this is given by a star here, a star notation, satisfies Fq of the fixed point is equal to 0. Okay, then we need first to draw F of Q. So we'll draw F of Q is V0 R minus Q RC. This is T, oh no, wait, this is Q and this is Q dot. So when Q is 0, F of Q is equal to V naught R, and FQ is gonna be 0, so FQ is 0 if QRC is equal to V naught R. Or in other ways, when Q is equal to V0 times C, and this is a fixed point, and this is gonna be happen somewhere in here. So now we just draw the line. Let's do it with red. So we do it as straight as possible. Wow, not bad at all. So this is the phase diagram describing the dynamics of Q, the charge. Okay, so we can understand now everything, at least from the point of view of this ODE. When we have the phase diagram, the next step is to draw the evolution in time of the charge. Okay, so we start to here, right here, the time. This is gonna be Q. So if our question was from a state of no charge, so Q0, so Q0. So here the charge is large, is at its maximum, but then little by little it decreases asymptotically until the fixed point. So we know that the fixed point is here V naught C, and as soon as it starts decelerating because Q dot start decreasing, so there is less and less current. Something like this. And this is just as you can, maybe we will see just in the next example. This is the case of an exponential, how you can reach a fixed point in an exponential way, also asymptotically. Okay, so we already have this example. We can go to another one right now. Okay, we will talk now about population growth, and this is shown in this way. When I'm talking about a differential equation, it's a good idea to always have this in mind. So you have a number of individuals, and this is the rate of change of the number of individuals. Call it, for example, people, a community of animals, or coronavirus as well. Okay, and this is just a parenthesis. I will show you something I did maybe in our meeting. As soon as this coronavirus showed up, I knew that the logistic equation, as we will show it in this example, was super clearly represented. So you will have the corresponding exponential growth, then somehow this deceleration, and then you reach eventually a fixed point when you have a number of people contaminated, and it remains like that for a long time. So this is, if you remember, maybe it's still like this. In China, they have right now like 80,000 people, yeah, with the coronavirus, or that have been contaminated with the virus. So this is actually somehow the fixed point, you see, in that sense. It reaches this stability, this equilibrium point. Of course, in the model of the coronavirus growth, I assume that there is a lot of complexity, but this simple structure is there. Okay. So just to tell you, so imagine we have first an equation where the exponential growth. So let's forget about this for the moment. So this is one of the most useful, but also classical ODEs. Okay, so I want you to remember that the growth of n is equal to, or is proportional to, n, which means that the larger n, the larger it grows. So this is actually nothing but exponential growth. And if you represent this in a picture, So in the evolution with respect to time, so you will have just sorry, this is supposed to be time. In this case, we will have our equation is going to be n dot equal r n, and then we will have, depending on the initial condition, let's something very small, then we'll have the exponential growth. Okay, and this is given by this growth rate, so it can be something like this, start smaller, like this, but this is still exponential growth. Now the trick, or the interesting part, is to model actually this growth rate. In this case, the growth rate here is constant, so we have considered r equal to r naught for all n. But a very smart of modeling this is as follows. So in here we can say that instead of this growth rate being constant with respect to n, maybe when the population grows, the growth rate actually decays, and eventually goes to 0 for a given k. So this is going to be called, as we will see it, the capacity of the population, which capacity has the population to grow. And therefore I want you to see that the structure is going to be the same. It's just n dot equal rn, but now r depends on n. And the easiest approximation is a linear decay of r. Okay, so based on this model, we have just the following: 1 over 1 minus n over k. So you will see that when k is equal, when n reaches k, this is going to be 1, and then it's 0, and you don't have any more growth. So this is the question we will now analyze. And you can think, how can you extend this model? I mean, I will be very encouraging all of you to see, in terms of coronavirus modeling, spreading of the coronavirus, how this R is modeled. So this is actually the critical part, how the growth rate is modeled. Okay, and this is the equation we just derived ourselves, and you realize this is a polynomial expression. So let me just put it, so r0 n minus n to the square over k. It is also of some help to make the derivative of n dot with respect to n, which is going to be r0 minus 2n over k. So it means that now we have the tools to plot the polynomial. Okay, we know that the function is 0 when n is 0. Wait, let me just put n here, n dot, when dot is 0, and when this term is 0, which is when n is equal to k. Okay, and now based on this derivative, then we will see what is the slope in here when n is equal to 0. The slope is positive because it's r. Therefore it has to be something like this, like a curve that grows and goes back like this. Okay, with all this oscillation, this is just my drawing. Okay, whatever, I just put it beautiful for the next slide. Sorry. As you see here, then we have the representation I just told you before, and I just plot everything that is positive, because it doesn't have any meaning to have negative values of individuals. Well, based on what you have seen before, then you expect that when you have a positive slope in here, we have a repeller, and we have here a negative slope, we have an attractor. Okay, with this we can already plot the expected evolution of the population and how it reaches the capacity K. We will select 3 points. Blue here. We will select a point when you have just started, you are in here, in this region. And another one when you are maybe reaching in here, so this is a given initial condition or something in here. Okay, let's put x0. Okay, I should just write another color. Let's put this was in red. Let's put x0 and the other one in white, yellow, x0. Okay, so let's draw this in time. Let's see how it evolves. Let's start with the easy one. So the easy one should be x dot, which is red. So the capacity K, what I forgot, I already screwed it up again. Why is this is supposed to be T N, and this is the capacity. Okay, so when we start, our population is in here at the initial condition. It just has to go to the equilibrium point. Okay, now let's go to the one which is blue. When we are just starting, and this is something I want you to pay attention at the starting point, we have almost like an exponential growth. It starts is slower, but it accelerates. But when it accelerates, then it reaches the maximum growth rate here, n dot, and then it starts decreasing again. So exponential growth and then decrease again until reaching exponentially the capacity. And another example is in this case when the population is just too large. So imagine you have too many cows and they can feed themselves because they are too much. Some of them will die eventually until you reach again the capacity, something like this. And now when you look at this, when I was looking at television and looking the growth, the initial growth, then the stabilization, so like a maximum growth rate, speed in here, and then a decay, there was a very interesting thing from data coming from China, for example. That was in February. So I fit some functions describing the growth rate with respect to n, well, with some little tweaks in between. But it's nice that how this model fits the data in a very nice way. So if you are interested, we can discuss this during the class. Is something very, very, very fundamental, but already contains the essence of the growth and decay. So as I speak right now, this is April 15th. So I'm 1 week before the starting of the classes. We have 120,000 infections in Germany, and I will see. I think we find ourselves almost like in this region. So hopefully, it's starting to decay already until giving a reaching a fixed point, hopefully 400,000, no more than that. We will see what the future show us. So this is figure 234 of in the book of Strogatz. So just you can refer to the book as well to read it if you want. Okay, so we have talked about attractors and repellers so far. And you already saw when we plot, in the case, for example, of x-axis x, in the y-axis x dot, you realize that the corresponding function, when we were at a positive slope, then we would have repellers. When the slope was negative, then we had attractors. So how can we actually show this in a more mathematical way? It's still very simple. Show you just in the next slide. So the basic idea is, okay, we have our function x dot equal fx, and we know already that a fixed point satisfies fx star equal to 0. Now the fundamental idea here is to decompose x, so by a fixed point and a little perturbation. So what we're doing is we will place ourselves in a position x that is very close to x star, but not exactly x star. And if the point just goes away from the fixed point, it means that you have a repeller. And if the fixed point, if this initial x goes back to the x star, so actually the perturbation just vanishes, we have therefore an attractor. So in here we just replace this, and you see that the x dt of the x star is 0 by definition. So it means that any change in x is because you have a change in the perturbed part of x. Okay, and now we also put the fx equal to fx star plus x perturbation, and when we just replace this in that function, we end up having the dynamics of the perturbation equal to fx star plus x hat. Now we will apply the Taylor expansion to this expression. Okay, so we have, as I said before, the equation describing the dynamics of the perturbation. We want to see if this perturbation grows or decays. Let's apply now a Taylor expansion to this, and I want to see if we remember how this is done. So we just say fx star, and what is the next term? Yeah, we have the derivative of f with respect to x evaluated where at the fixed point, so x equal to x star, and here the distance, so delta x, which in this case is nothing but the perturbation x hat. And we can go to the higher order terms, but for the moment we'll just consider only antilinear terms. Okay, this equation can be simplified. How? Because we know that by definition this term is 0. Okay, so basically this is 0, and we just end up having a very simple expression to understand the dynamics of the perturbation, and this dynamics depends exclusively on the slope of f with respect to x. So let me just write in here. Okay, this is an approximation because now I'm not considering the truncation error. Okay, so this is the final result. So this equation, and this is a linear ODE, which is nothing but the linearization of this equation around x star. And now I want you to always remember things in terms of the thing I just showed you before. For example, with the for the population growth, we have this expression, and this is just governed by the growth rate. Okay, so if you remember this example, and now you look at this equation in here, what is the growth rate in here? Okay, the growth rate is nothing but this slope. So if the growth rate is positive, if you remember actually how the solution of this equation looks like, it's like something like yeah, with a constant and then an exponential growth rate with respect to t, and this is in this case the growth rate. So if it is positive, it will go and increase exponentially. If it's negative, it will decay in an exponential way. And that's why the mathematical explanation of the slope, how the slope defines the growth rate of the perturbation, and therefore how it defines if a given fixed point is an attractor or a repeller. Okay, so we have already seen this situation, but there might be a case when it happens. So imagine a given function, so x dot, imagine a function like this that goes, touches the axis, goes away, and here is already at one point. So based on this equation, we have the fixed point in here. Let's put it in black better. And then it means that according to this equation, the system is stable if I perturb it to the left or to the right, it doesn't matter, which is actually not the case, because when we do this linearization, we are actually neglecting all the high order terms in the expansion. And in this case, when we have this first order term being 0, the second order term, the third order term, they get some importance. So from this you cannot say that this point is going to be unconditionally stable. As we will see maybe in the next class, yes, we will see that this is actually the case of a half stable point. So this, I will just maybe tell the story right now. Imagine you have a region in here and another region in here. Maybe here let's put it red and here blue. So if you perturb this particle to the right, it will just go away. So in this case you will have an attractor from a repeller from this side. But if you perturb the particle from the left, it will go back again to equilibrium. So in this case you will have an arrow in this direction and an arrow in this direction, and you will see this is the way you draw this half stable point. So half is black, half is white, and this is not defined by this. Okay, so just be aware about that. So now we finish this session talking about the existence and uniqueness of a solution. This is very important because we want to create a bound where our analysis is valid. Outside from this set of conditions, our analysis doesn't make any sense. So the idea is that every single ODE we are analyzing exhibits an unique solution. Imagine we have a face portrait as we just pictured before. We have x dot, and we have an initial condition x naught here, but we have this kind of extreme situations in which we have actually two trajectories getting from this initial condition. So basically we have not a unique solution because we have two possibilities. Either we go in this trajectory or we go in this trajectory. And this is something that we want to avoid. Actually, these are very special cases. So we want to see which are the conditions that get us avoiding these kind of situations. Okay, this is an example. Imagine we have this solution or this function which is just the square root of t, and if we picture this in just in a time figure, so we have x, this time x is the y axis, so we will have actually the same situation as just before that we showed with the face portrait. We have an initial condition and two possible evolutions, and this is actually something we want to avoid, or to understand which are the conditions to be able to avoid this kind of solutions. So if we go and we analyze the actual partial differential equation that led me to have this kind of solution, is nothing but this equation. So if I write, for example, such an equation, if I write something like x dot equal to 1 over x. So here we have the solution, how we picture this in the face portrait of, so this one here. Okay, and you will see just in the next slides that is also important to picture this one. Okay, and you see that here we have something goes to infinity. So basically this function fx is not defined at x equal to 0, nor is defined the f dx are x equal to 0, or both of them are not defined at x equal to 0. This is another example in which we have this situation. So we have an initial condition, and then we just have two possible trajectories that it follows. So similar as before, we can just express this, so just x equal fx, so x dot is equal to x1 over 3. So this one will produce this solution x here. And when we picture the solution, so we have a function fx, this is the f dx, that is actually not defined at x equal to 0, and also here the fx, this is actually defined f(x) equal to 0. Okay, so this is not exactly the same as before, because here we know that f at 0 is 0. Okay, so having a function that is not defined at a given point might be maybe not the condition, because still this function that is defined here can produce this sort of situation. So what is the actual condition we have to take into account? So we have these two questions. What is common in these two examples? Which conditions do we need to assure uniqueness of the solution? So we need two conditions. We need that both fx and the f dx are continuous in an interval in x. Okay, so this is actually the condition. Now I want to to perturb you a bit. So if we go to the next slide, and we see this, okay, this is something we just saw before, so it was the previous slide actually. So if we look at this, we say, yeah, okay, this fx is actually, sorry, this is, yeah, this is fx is actually continuous. Okay, so this is continuous. What about this one? This is a continuous function. Okay, some of you will say, of course it is continuous. Okay, but I want to be like the devil advocate and say, why it is continuous? Because if you see here, you follow the point, this goes towards infinity and this also go towards infinity, so the both of them meet at infinity. So this is continuous, no? Because if both of them they go towards infinity, so what do you have to answer? So there is this situation is interesting because there are many times that students get somehow like confused, like what is going on, okay? And this becomes because this definition of continuity has to be rigorous, and this is how it goes next. So what is a continuous function? A function is continuous at c if it's both defined at c and its value at c equals the limit of f as x approaches z. Okay, so basically is the following. Is like the delta epsilon definition of a continuous function. So if you see here, I will just picture this as before. So we had this kind of situation. And this goes to infinity. So we see here that the x minus a, so in this case our a, what is this? Our a is 0. So when x goes small, so when x goes to 0, so this is something that is bounded. This is bounded or not? So let me just show you here. For example, if I have, this is the interval I'm looking in here, and the other interval that I'm looking is therefore the corresponding function here at this point. So this interval. Okay, so now imagine that you are decreasing the black line, so it's getting shortened and shortened, and this blue line is getting larger and larger. Okay, so for a continuous function to exist, we need that when this goes to 0, this one remains bounded. But this is not the case, because when this x goes to 0, this is unbounded. It doesn't have any limit. It goes to infinity. Okay, so based on that, on this definition, this function is actually discontinuous at x equal to 0. I want to also refer to a note by passing, really not related to this, not much, but it's about how you write actually this kind of situation. Sometimes you find it in books. So this kind of situation, so many people say, yeah, okay, this is actually equal to infinity. But looking at this kind of notation, or how you write this, is actually very perturbing, because it means that we are under the, let's say, real numbers in classical algebra. This means that this is equal to this, and this is of course something wrong. So infinity is not a number. Infinity is like a concept, and actually that's why I prefer to say that the function this is not defined. So x over 0 is not defined, it doesn't exist, okay? And this is how you should interpret this infinity. Okay, let me just scratch this thing. It's better to say x over 0 is not defined. This is the way to say that. Much better. Okay, now we will talk about the impossibility of oscillations in one-dimensional systems. And this is something that at first glance seemed to be, well, an additional subject, let's say. But this is actually very interesting because you will think that let me tell you two things. You have a system, and here you have a system, and now we have an input to the system, and we have an output. Let's call this thing okay, let's put here red, and this is the red system, and here black, or let's put it blue just to differentiate, and this is the output. Okay, so let's assume now that this system is described by one dimensions, let's say one ODE, and this system is described by two ODEs or more. Okay, so in a linear system, I don't know if you remember that from your courses on control, you have this kind of situation. Imagine you have here time, and this is the corresponding answer. Let's put here y. This is the input u, the output y. Okay, so now let's assume that we send an impulse in u. If we send an impulse in u, we will have the input response of the system. And the thing is that the input response of the system in this one dimension, so when we have one ODE, has two possibilities. Either it diverges, so maybe this will have some situation like this, so from 0 grows exponentially and blows away, or we have an initial condition that, so the perturbation that decreases exponentially. So let's picture this second case, when you have a situation when you have a perturbation that decreases exponentially, and this is the input response of a one-dimensional system. Now when we go to a second order system or larger dimensions, 3, 4, whatever, so we have situations that you can also have something that doesn't oscillate, but we may have also something that oscillates. So we can have a situation in which you just send a perturbation, and the system will go like, okay, will react to this, and little by little oscillation will actually decay to the equilibrium point. Or you have the other situation when you have oscillations and they just grow and they blow away. Okay, so from now on, please remember this concept. If you have a system that is described by one ODE, there is nothing else, there is nothing like this, okay? Never. A 2D, yeah, you can have it. Actually, this is something we will see when we go to two dimensions. Here, just to point out, when I mention one ODE, it means one differential equation of first order, and two ODEs, an equation of second order, which can be represented by two ODEs of first order. So this is just a parenthesis, let's say. Okay, let's talk now about potentials. This is another way of looking at the system. So here we have the description of fx equal to minus dv dx, and we have defined this v to be a potential. If you want to think about potential energy, maybe can be of some help. So now instead of pointing here x dot x, we are writing vxx. Okay, this is different. And we have this a given example. So you remember that for the fixed points, for a fixed points to have to exist, we need that fx is equal to 0, which means in this case that dvx is equal to 0. What does it mean? That we actually are looking at a minima or maxima of the potential function. So we have here a minimum, or here we have a maximum. So this has to be a fixed point or related to a fixed point. This is actually related to a fixed point. In addition to that, is it possible to establish that a fixed point that is in a region that is concave, then we will have a stable fixed point, so an attractor. So one that is convex is gonna be a repeller. Okay. And now something very silly, but actually is of interest. Now you can realize that, imagine you have here a little let's say ball. Okay, so you put it in here, and it's actually very sensitive to any perturbation. If you just hit it a bit, it will just go away from the fixed point, and it will go towards the actual attractor, which this is gonna be the attractor. Okay, and this is gonna be the repeller. In order, when you're picturing this in your minds, you have to remember that we don't have oscillation. So you could picture this in your mind like this, that you just kick the ball, and the ball goes like this, and then go like this, and then go like this, and it's oscillating until getting into this point. This is actually wrong if we are talking about one-dimensional systems, as we just pointed out before, because the thing we have to imagine is that we just kick the red thing even with a very high kick, let's say, and it goes fast, and little by little it decays exponentially until reaching the equilibrium point. So this is the way we have to really imagine this. So let's go just do some quick derivation. So we have f is equal to minus dv dx, and we know this equation already. So this is x dot equal fx, which is equal to minus dv dx. Okay, and now we do something, we do this trick. So this chain rule. So we have dv dt is equal to dv dx dx dt. Okay, we just put this thing denominator numerator, and now we're able to replace. So dv dt, we have dv dx, and we have the x dt, and the x dt is nothing but minus dv dx. So basically dv dt is gonna be minus this to the square. Okay, and this is a negative value, which means that the potential decreases with time. So you are you were in this fixed point as before. So let me just put it in black. So it was something like this. So we're here. You kick it, and the potential it doesn't remain constant. The potential decreases all the way until reaching the attractor. The interesting thing to see here is that a particle always moves towards regions of lower potential, which is actually attractors. Another consequence of this is that when you reach the equilibrium point of the attractor, the potential doesn't change anymore. So in this case, we will have dV dt equal to 0. And because of the definition of before, that dV dt is equal to minus dV dx to the square, we see that dV dx has to be 0. Okay? Basically, the potential is then constant. Okay, let's do just a quick example to finish today's session. And this is gonna be the ODE we want to study. Okay, we could do it by hand, why not? But why not to use the tools that are available on the internet? And I like one that is called Desmos. I will show you it in the next slide. So you just go to Google, you type Desmos. I really encourage you to explore this. And then you just go into the graphing calculator. And this is how it looks like. Okay, I just forgot how was the function. Let me just remember it. Okay, so we will have just type in here x. So in this case it's going to be, okay, I haven't seen this thing before, x. So you see here already that you have the graphic minus x to the square. Okay, so x to the x minus x to the cube. So this is how it looks like, this function. Okay, so we have how many fixed points already? So just please let me know. Okay, we have 3 fixed points, so 3 regions in which the function crosses the x-axis. We have, this is an attractor or a repeller. This is a repeller. Remember, we have a positive slope here. Here, this is a negative slope, a negative slope. These two are attractors. Okay. Okay, now let's draw the potential. So we have to integrate this function. So we can just do it like right now. So the integral of x is what? So it's x to the square over 2. Wait a minute, I have a problem with this. This is x squared over 2 and now we have minus x to the cube. Then we will have minus x to the 4 over 4. Let me just write this thing here. X 4 over 4. Okay, here is actually 4. Okay, so this is like this. We did a mistake. What is the mistake we just did? Because right now everything is upside down. Yeah, we actually miss the minus because we have minus dv ds minus dv dx is equal to fx. So we have to put a sign in here. So this is gonna be minus, and here we have a plus. Eccola. So we have what we were looking for. Now if we just here, this is actually the repeller. So you'll see that in terms of potential, you have a kick and it will just go away from a region of lower potential until reaching the equilibrium point, which is nothing but the fixed point in here. Okay, so this is the concept of potential. It's another way of looking at systems. Okay, so we are done with the class of today, the session 2. The next session, the next video, is going to be about something very very nice. It's about bifurcations. Okay. Well, so see you on Thursday at the class, and we discuss all this content of today. So please look at the video, get your questions, because the class is going to be only about discussion. It's not going to, I will not repeat this. Okay, we will just discuss the video and the possible questions. Okay, so bye bye.